So last time we talked about relating our angular variables to our linear variables, and we'd already done this for tangential velocity, and the next thing we wanted to do it for was tangential acceleration. And so we showed, oops, going the wrong way here. We showed last time that the tangential acceleration was the radius times the angular acceleration. And we just did a trivial little example here. So tangential acceleration, of course, when we've got motion in a circle, is not the only possible direction for motion, right? If we've got an object moving in some sort of path here, and it's a circular path, then we've got a tangential velocity. So we have a velocity here, and we have the tangential acceleration if we have an angular acceleration, right? That was what we talked about last time, was r theta double dot. But of course, for any object that's going round in a circle, we also have a centripetal acceleration, right? If you remember the cart example from the midterm, right? We have an acceleration towards the center here, right, in this direction. So this is a tangential acceleration. These are accelerations, not forces, right? So, sorry, not tangential, centripetal acceleration. And we said that the centripetal acceleration was equal, the magnitude of the centripetal acceleration was the tangential speed, right? Because before we only talked about we had a constant speed. So at any one instant in time, the centripetal acceleration is going to be the square of the tangential velocity divided by the radius of the circle. And so that was writing it in linear variables. But of course, since we're doing rotational motion now, and we've developed these angular variables, and we're expressing everything in terms of angular velocity and angular acceleration, we want to be able to also write this centripetal acceleration in terms of our angular variables. And so for this, we remember that we can express our tangential velocity as r times omega, where omega is our angular velocity, right, and r is the radius. So if we look at this, we can see that the centripetal acceleration is r squared omega squared divided by r. So of course the r's cancel, and what we end up with is a centripetal acceleration in terms of our angular variables as r omega squared, or r theta dot squared, right, whichever way you want to write it. So the thing we now have to remember when we've got our a non-uniform circular motion is that we now have two components of acceleration. We have a tangential acceleration, which is related to the angular acceleration. So that means that our speed, if you like, is increasing as we go around the circle, or decreasing. It's changing in any way, right? So we have an acceleration that's tangential, but we also, because of course we're going round in a circle, we still have a centripetal acceleration, and that will change with the angular velocity. And so we can relate, we've got two components of acceleration now, no longer just a central component. We've got a centripetal, and a tangential component. So we can do now problems. So if we turn back to our catapult example, which we did very briefly before, we can now ask ourselves, what is the magnitude and direction of the acceleration that the boulder on the end of this catapult that's being accelerated now feels? Oops, what's that? And so when we're doing this, remember that this catapult arm, we've got this counterweight here, it's accelerating the boulder around in a circle. So we not only have this tangential acceleration here that we calculated before, we also have this centripetal acceleration. So we've got these two components of acceleration because we have non-uniform circular motion. So what we've got, if I draw it here, is we have our component of acceleration here, tangential, that's equal to r theta double dot, and we have a centripetal acceleration here that is equal to r theta dot squared. And so what we want to do is, if we want to calculate the magnitude and the direction, well, clearly these two things are at right angles. This is radial, this is tangential, and so they're always at 90 degrees to one another. And so what we can do is we can combine these and say, here's our centripetal acceleration, here's our tangential acceleration, and so our resultant is in this direction here, and we'll say that's an angle phi, and of course this angle here, this length here is just AT, right? So that's a badly drawn rectangle. So if we look at this, we can say that the tangent of phi is equal to the opposite over the adjacent, right? And remember that this centripetal acceleration is along the arm of the boulder, which of course will be changing direction with time as well. So, but we have tan phi is equal to AT over AC, and that is equal to r theta double dot divided by r theta dot squared. So the r's cancel, and we just have theta double dot over theta dot squared, right? So, or if you want to write it in the other variables, alpha over omega squared. Either one, right? It doesn't matter which way you write it, it means the same thing. So angular acceleration divided by the angular velocity squared. So if we look at this problem now, we've got our angle here, but what we now need to know is we know the angular acceleration. Remember, we were told that earlier. And so what we need now, so we know this quantity, we're told it, what we need now is we need to know what the angular velocity is as a function of time. Since we've got a constant angular acceleration, we can go back to our constant angular acceleration equations, and we've got this one here, right, where omega is equal to omega naught plus alpha times time, right? Well, we start at rest, so, well, I write down the things here. So we've got omega naught, omega, alpha, t, and theta. So omega naught we know, because that's equal to 0. We start at rest. Omega is what we want. That's what we want to find out. Alpha we know because we're told. And time, we want that in there because we're told to find how the angle changes as a function of time. So we're going to need a time in there. And then, of course, we don't care about the actual angle that we've rotated through. That's not important to us. So if we use this, we're going to end up with omega is equal to alpha times time. And so we can put this in here. So tan phi now is equal to alpha over alpha times alpha squared times time squared. So the alphas cancel, and we get 1 over alpha times the time squared. And since the angular acceleration is 5 radians per second squared, then this is 1 over 5 t squared. And so that tells us how the angle of the acceleration will change over time with respect to the boulder, with respect to the arm, sorry, of the catapult. And if we go back to the drawing here, right, what this tells us is that since we got an answer of 1 over 5 t squared, as t increases, this is going to get smaller. And so the inverse tangent of a number that goes towards 0 is 0, right? So as the tangent decreases, so will this angle phi here. So we can check to see whether that makes sense. Well, what it's telling us is as this thing starts to move faster and faster around in a circle, the net acceleration will point more and more along the line of this arm, which makes sense because if we look at this, the tangential acceleration is constant. Both of these quantities are constant, the radius and the angular acceleration, whereas here the centripetal acceleration depends on the angular velocity, and so as this thing rotates faster and faster and faster, the centripetal acceleration becomes more and more important, and this acceleration will point more and more along the line, right? So as it goes faster and faster, it will point more along here, and so we do expect phi to decrease. It'll never go to 0, and if we look at this, we can see it will never go to 0 unless after an infinite amount of time, right? So this is exactly what we would expect. I mean, it doesn't tell us that the answer's right, but at least tells us that conceptually it obeys, it does what we think it should, which is it gets smaller over time and never actually goes to 0. So that's good. right? It has the right sort of features. So next step is to calculate the magnitude of the acceleration. So I'm not going to go through this here because it's just a lot of boring algebra. But all we do for this, right, is we've got our triangle here. And so we just use Pythagoras on this triangle. The length of the hypotenuse is AC squared plus AT squared, square root of. So we just put all these things together, take the square root, and after all of this algebra, we end up with the magnitude of the acceleration is 15 times the square root of 1 plus 25t to the power 4, which again is what we would expect to be the case because now it's going to increase roughly as t squared because it's the square root of something t to the 4. So it will increase roughly as something like t squared. And so again, that's what we expect. We expect the acceleration to increase because not only is it going to be going faster tangentially, it's also going to be fast. It's also going to have an increasing. It's not only going to have a constant tangential acceleration. It's going to have an increasing centripetal acceleration as the lever arm swings faster and faster. So again, we expect the magnitude to increase. So that's good too. Okay. So any questions on that boulder? Right? Just remember, you've got two components now of acceleration, centripetal and tangential. Right? As long as you have a non-zero angular acceleration, you will have a non-zero tangential acceleration. Okay, so another example. Supposing we have a car that drives from Edmonton, which is at 53.5 degrees latitude, roughly, and it drives due south. We'll assume the Highway 7 is Highway 2, sorry, or the QE2 highway now, I suppose, is a dead straight line going south. And so it drives south to Calgary, and Calgary is at 51.7 degrees latitude. So we're told the radius of the Earth, and what we're asked is what are the initial and final tangential speeds due to the Earth's rotation? Right? So we're going round the surface of the Earth, and we're asked what is going to be our change in the tangential speeds due to the Earth's rotation. And then we're asked what is the average easterly acceleration if the trip takes 3 hours. And last question is, what would happen if instead of a car, we considered a wind that was blowing due south at Edmonton? So this is the picture we need to draw. So if we look at this, here we've got a picture of the Earth with a line of latitude shown here, and this is the definition of latitude, right? You take your position on the Earth, you measure the angle between the position, the line that joins your position to the center of the Earth and the plane of the equator, right? That's the definition of latitude. So if we look at this, we can see that as we move further south, our radius, the radius of the circle that we're standing on, is going to be changing. Right? So I will grossly exaggerate here. What we've got is here is our Earth with our equator on it, right? And so here is Edmonton and here is Calgary. So I just moved Calgary into the tropics. Not that funny. Okay, so what we have is we have our two latitudes here. So theta E and theta C for Edmonton and Calgary. And what you can see is that somebody at Edmonton is moving on a circle that looks like this, whereas somebody at Calgary is moving on a circle that looks like this. And so somebody at Calgary is moving faster than somebody in Edmonton, simply because we know it takes 24 hours to go once around the Earth, right? Because that's how long a day is. So it takes 24 hours. So somebody at Edmonton, because we're nearer to the pole, moves a shorter distance than someone at Calgary. Of course, the extremes are somebody standing on the equator and somebody standing on the North Pole. If you're standing on the North Pole, you're just sort of rotating around on the spot. It doesn't make you dizzy, though, so that's okay. But you're just rotating around on the spot, whereas if you're down on the equator, you're actually moving thousands of kilometers in the period of 24 hours. So there's clearly going to be a difference in your velocities, and that's why, I think I mentioned earlier, that's why you launch satellites from as near the equator as you can, because you gain you gain a large amount of velocity simply because you're near the equator versus near the pole, right? You'd lose a lot of kinetic energy if you tried to launch something from the pole rather than on the equator. Okay, so we can calculate the angular velocity is simple, right? Omega is 2 pi divided by the period, and we know the period is 24 hours, and so if you put the numbers in there, it's shown there on the slide, you end up with 7.27 times 10 to the minus 5 radians per second, right? So that's our angular velocity. And the Earth being a rigid body, that is the angular velocity of every point on the Earth, right? We talked about that with that disk and points A and B, right? It's the same for everybody. Everybody does one rotation in 24 hours, and so you all go through 2 pi radians in a 24-hour period. So that's our angular velocity. But our tangential velocity, right, is going to be equal to omega times r, and clearly there's going to be a difference between Edmonton and Calgary here. If we look at this point here, what we want, if this is the axis, right, what we want to calculate is that radius there, right? If we look at this line, it's a little bit crowded, this diagram, I'm afraid, but it's the same one that's on there. So if you look at this line, this is the radius of the Earth. We're assuming it's spherical. And so this line here is just r cosine theta, right? So if I drop this vertically down here, you can see this length here is the same as the radius. So the radius that you go through here, this is omega times r, which is the radius of the Earth, times cosine theta, where this is your latitude. And this is radius of the Earth. Right? And so that tells us we can use that formula now to calculate our tangential velocity on the surface of the planet. So if you put in the numbers, we know the radius is very large. We may have a very small angular velocity, but there is a very, very large radius. It's thousands of 6,000 kilometer radius. And so if we put that in there, what we find is that the tangential speed at Edmonton, with a latitude of 53.5, is 276 meters per second. So as we stand here, right, we are hurtling through space at 276 meters per second, right? So that's multiply that by 3.6, and that's 800 miles an hour, kilometers per hour, right? So, a few hundred kilometers per hour while we stand here. Of course, we don't notice it because everything around us is traveling at the same velocity. So similarly, if we go to Calgary, we can stick in the lower latitude of Calgary here, and we find that Calgary is moving faster than Edmonton. It's moving at 288 meters per second. Now, that doesn't mean that we're going to sort of get they're going to zoom past us and head off into the east. It's simply because they are lower down on the Earth's surface, and so therefore going around in a bigger radius, right? So it's the effect of being on a spherical, on the surface of a sphere that's rotating, right? So Calgary is moving faster. So now we can go back to the question, and that is, what is the, so we've calculated the velocities, the eastward velocity of Edmonton and Calgary, and so now we can calculate the average acceleration in the eastward direction during the journey. Well, the average acceleration is just the change in velocity divided by the change in time. Well, that's 288 minus 276, and we divide that by 3 hours because the journey takes 3 hours, and so you get an average eastwards acceleration when driving from Edmonton to Calgary of just over 1 millimeter per second squared. So it's not noticeable. It's not going to have you plastered up against the side of your car due to the huge forces involved trying to give you this, right? I mean, if you look at this, it's almost just over 1,000 times less than the Earth's gravitational field. So the force that you need to produce this is 1,000 times less than your weight, and so you aren't going to notice something like that, right? It's a very, very tiny force. However, because basically you're sat here and there's friction between you and whatever you're sat on. And if you think about it, if you look at the coefficient of friction, you need a coefficient of friction of about 0.001 in order to provide this sort of acceleration as you're driving south. So it's peanuts, right? However, what would happen if you had the wind? Well, the wind isn't fixed to the ground, right? It's not like you and I when we're driving south in a car. You are not, the frictional forces are very, very small. It's just due to the viscosity of the air, and the viscosity of the air is very, very low, right? So the car doesn't notice this because it just has a small tangential, a small easterly component of friction if it was driving on a perfectly south-facing road. But the wind doesn't have that, right? It doesn't have that level of friction. So what happens is the wind does not accelerate in the eastwards direction. It keeps on with, if it's blowing due south at Edmonton, it has an eastwards velocity of 276 meters per second. And by the time it reaches Calgary, it still has the same southerly velocity of 276 meters per second. But now the ground underneath it is moving more rapidly towards the east. And so what happens is, although the wind is heading that way at 276, the ground is heading that way at 288. And so relative to the ground, it looks like the wind has a component of its velocity towards the west. So what happens is, as it starts, so here we have Edmonton, and here we have Calgary. If we have the wind blowing due south at Edmonton, right, when it gets to Calgary, it doesn't have enough velocity to be heading due south because the ground now is moving faster. The wind's velocity has not changed. It's the ground that is moving faster to the east. And so what happens is you have the same southerly component plus you have a small westerly component because the ground is now moving faster to the east than the wind is, with the result that the wind looks like it's moving in a direction like this. And so what happens is you end up with the wind following a path that curves around, and eventually what will happen is this will carry on, and as it heads north, it will also be going backwards, and so you end up with this circular pattern here. And that is why we get if you look on the weather maps, you end up with rotating weather patterns on a very, very large scale, right? It's because of the differential speeds between the air and the ground. The ground is rotating with the Earth, and it so rotates at a fixed, as a rigid object. The air is not coupled to that, and so as it moves south, it finds that the speed of the ground underneath it is changing. And so although the air pattern is sort of going in a straight line, because we measure the air relative to the ground wherever we happen to be, it looks like the air has shifted direction and has moved off and eventually curls up, and you get these large circular weather patterns. And it also explains why they curl one way in the northern hemisphere and the opposite way in the southern hemisphere. If this was in the southern hemisphere, then of course as we move down here, Calgary would be, as we moved south, Calgary would be rotating more slowly than Edmonton if Canada was in the southern hemisphere. And so therefore, because the further south you go, you get closer to the South Pole. And so therefore, of course, the wind would curl in the other direction. And so that's why you get these, it's called the Coriolis force, and it's why you end up with the rotating weather patterns. Things like hurricanes will rotate one way in the northern hemisphere, they rotate the other way in the southern hemisphere. So this is a picture of, I think this is actually a hurricane. So you can see it's rotating around, but it's hundreds and hundreds of kilometers in size, right? So the one thing you sometimes see when people talk about this Coriolis force is, oh, that's the reason why the water in your sink rotates one way when you pull out the plug in the northern hemisphere versus the southern hemisphere. That's utter rubbish, right? The Coriolis force, as you've seen, is a tiny, tiny force, right? Over the length of driving from Edmonton to Calgary, it was 1 millimeter per second, driving at 100 and some kilometers per hour. So in the size of your sink over the space of about 1 centimeter, the Coriolis force is not noticeable compared to the thermal motion of your water molecules. So it does not explain why water spirals in a sink. That's just due to eddy currents and nothing to do with the Coriolis force at all. It does explain why wind patterns curl up one way or the other way in the northern or southern hemispheres. So just to show you that you can actually bring the Coriolis force down to size, what we've got here is a video, and so this was my grad student getting dizzy on a turntable. So what we did is we've got a large turntable that we will eventually be able to do demos in here when the physics department's moved into CSIS, but since we're stuck halfway across campus, it's too big to move. And so what we've got is this is a rotating turntable, and we've got two grad student and one of our UGL technicians are going to roll a bowling ball backwards and forwards across this table. Now, to start with, what I'm showing you is a camera that's mounted on a step ladder that's stationary and looking at the rotating table, and you'll see that the bowling ball moves in a straight line when they roll it. In the second half of the film, what we do is we move the camera onto the table, right? So that's like a camera that would be here on the surface of the Earth. So we move the camera onto the table, and you can see that the ball, instead of appearing to go in a straight line, suddenly appears to curve. And I didn't show you the footage of when they first started doing this because they weren't expecting the ball to curve, and so the ball went all over the place and kept falling off the table. I'll just turn off the sound. But you can see here, right, it moves in a straight line, right? So it's just doing normal, there's no forces acting on it, it's the table rotates underneath it, but the ball itself rolls in a nice straight line, right, according to Newton's first law. So there we go. Now watch what happens. This is with the ball on the table. I don't know if you guys can see that. Is it visible? Can you see it? I'll turn down the lights some more. It'll go a bit dark now. Okay, so you can see that the ball appears to be curving now, right? I mean, it appears to sort of curl there to the top. There, right? So if you're on the rotating frame, it appears that it's curling, and the reason for that is that you're rotating about this point here, and as it rolls further out to here, the table is moving faster this way, and so it appears that the ball slows down and starts moving that way, right? But you saw from the stationary camera that this ball is moving in a straight line. It's not moving in a curved line at all. It's only that you're in a rotating frame that it appears to move in a curved line, right? So you can see it come in and curve around here, right? It's not actually moving in a curved line, it's moving in a straight line, and, oh, these are the outtakes. Yeah, that was the outtake. Okay. Yeah, see, it's difficult to do, so what we try and do when we actually can get it in here is get a couple of you guys to try it out and see how hard it is. Because it is tricky because you're not used to it, you're not expecting it to curve like that. Okay, so that's the Coriolis force. So just like the centrifugal force, that is what we call a fictitious force, right? You can model it as a sort of sideways force on a wind current, but it's not actually there. It's simply due to the fact that you're in an accelerating reference frame. Okay, so let's do another example, right? So we've got now a mass of 1 kilogram placed on a turntable that's gradually accelerated from rest at an angular acceleration of 1 radian per second. The coefficient of friction is 3.5. The object's 1 meter away from the axis of rotation. And the question is now, how long is it before the object moves? So how long do you have before the acceleration of the disk has, causes the object to move? So here we've got two components of acceleration, right? Remember, we've got an angular acceleration here, which means we have a tangential acceleration for the object. And we're going round in a circle, so we also have a centripetal acceleration. And the only force acting in the horizontal plane on the object is a friction force, right? If you look at this sideways, what you've got is here is the rotating table. You've got your block on it. It's rotating about some axis here. You've got your block, right? So you have a normal force acting upwards. You have a weight acting downwards. And the only force you've got left to act in a horizontal direction to make it rotate about this axis is a friction force, right? So, and those are the only forces acting on it, right? So remember, if you remember back to the midterm, we don't add a centripetal force. We go through, what forces we know can exist. So if we look at here, we've got a contact between two objects. So we've got a contact between two objects, which means we can have a normal force acting on the object that's perpendicular to the surface of contact and points away from it. So that's the R. We also have a friction force that's parallel to the plane of contact and acts to stop relative motion. So if this wasn't here and this thing started rotating, then what would happen is this object here would slide on the surface, and the only way it will not slide on the surface is if the object accelerates the same as the surface underneath it, and for it to do that, it must accelerate towards the center of rotation and in a tangential direction as well, right? Because remember, we're not just talking uniform motion, we're talking angular acceleration as well. So if we look at it from above, this is our axis of rotation here, and this is our block, and we're going to be having an angular acceleration alpha in that direction, which means that we have two accelerations here. We have our tangential acceleration in this direction, and our centripetal acceleration in this direction, which means the friction force is not pointing straight towards the center. It's not pointing in a tangential direction. It's pointing in some direction like that, right? Depends on the sizes of these two components. Just like we saw with the boulder on the catapult, it's exactly the same thing here, right? We have to have a force providing a tangential acceleration and a centripetal acceleration. You've got to provide both, and the only force acting in the horizontal plane is friction, and so therefore friction has to provide both these components, which means it has to act in a direction like this, right? It's not acting straight towards the center, it's not acting tangentially, it's got to act somewhere between the two so that there is a component of friction to provide this acceleration and a component of friction to provide this acceleration, right? And so the way you should be thinking of this is you've got these two accelerations, you know that they're there, so there must be a force producing them, and the only force that we know will produce them is the friction force, because that's the only force acting in the horizontal plane. We don't start adding in accelerating forces or centripetal forces. Those are just the job descriptions. So, if you look at this, then this component of the friction force has the job description of being the centripetal force, right? But it's not some extra force we add. Right? It's got to come from a known cause, in this case friction. So we've got to calculate now both these tangential and centripetal components. So the tangential acceleration is easy. It's the radius times the angular acceleration. Well, we're told the radius is 1 meter. Angular acceleration is 1 radian per second. So the tangential acceleration is 1 meter per second squared. Centripetal acceleration is omega squared times r, so we have to do exactly what we did with the boulder in the catapult, and we use our constant angular acceleration. We're told it starts at rest, and so this is 0, and so we just have the angular acceleration times time, right? And so that gives us our angular velocity. And so, just again, it's exactly the same sort of thing we did with the boulder. The magnitude of our acceleration is we get from Pythagoras, because these two components, the tangential and centripetal, are at 90 degrees to each other, so we can use Pythagoras to add them together to get the magnitude of the resultant. And so we just use Pythagoras here, and this is 1, and this is t squared, and so we just end up with, and so we're squaring both of those, so 1 squared is 1, t squared is t to the fourth, and so we just take the square root, and so this is the magnitude of our acceleration. So at this point now, we did exactly the same as we did with the boulder, right? The numbers were different, but the method was exactly the same. The difference now is that we have a force that's providing this acceleration, and so we use Newton's second law. So we know that force is equal to mass times acceleration, so the frictional force that we require is just m times the net acceleration, which is 1 plus t to the fourth square rooted, right? So that's our, that gives us our expression for the frictional force. But of course, we can relate the frictional force here to the normal force, right, using the coefficient of friction. So if we look at this diagram here, what this tells us is that in the limiting case, because we're asked how long is it going to be before the object moves, in the limiting case, the friction is equal to mu times r. And if we resolve the forces vertically, there's no vertical acceleration, so the sum of the forces vertically must be 0. So Newton 2 in the vertical direction gives us that r is equal to mg, and so we end up here that the frictional force is equal to mu mg in the limiting case, right? So just as the object's about to move, the frictional force here is mu mg. So this here is equal to mu times m times g. So first thing that's important is the mass of the object doesn't matter, right? That cancels out. And now we know mu, we know the acceleration due to gravity, and so we can just solve this equation, right? You square both sides, and you get 1 plus t to the fourth is equal to mu squared g squared. And so you rearrange that, t to the fourth is equal to mu squared g squared minus 1. And so therefore t is equal to the fourth root of mu squared g squared minus 1. All right, and so that's how you solve it. And if you stick in the numbers, you end up with 5.85 seconds, right? So 5.85 seconds after the turntable starts, the frictional force will not be sufficient to keep the thing moving with the rotating table, right? So it's the same sort of thing we did for the boulder. There's just this extra step now to relate the force to the magnitude of the acceleration that we've calculated, right? And the other difference here is that we have a tangential acceleration as well as a centripetal acceleration. Any questions on that? Yeah. Sorry, the movement is? Moving around. Yeah. No, okay, so when the friction fails, right, so once the frictional force is maxed out, and then what will happen is then the object will move, right? But until the frictional force is maxed out, the object will stay stationary relative to the rotating disk, right? So what happens is the frictional force, the frictional force will slowly increase as the disk starts to go faster and faster, because this centripetal component here is going to increase. This is constant, but this component here will increase with time. And then at some point what will happen is the frictional force will not be large enough to be able to provide that acceleration, and so at that point the object will start to slip, right? So the frictional force will still be there trying to stop the motion, but it won't be enough to actually stop it. And so what will happen is this thing will not have the required centripetal acceleration. So it won't just move off in a straight line because friction will still be acting on it. What will happen is it'll sort of move, its radius of curvature will become larger than 1 meter, and so it'll sort of move off in a curved line like that, sort of, right? So any other questions? Good, okay. So that's it for what we call rotational kinematics, but just as we had one linear kinematics, that was followed by linear dynamics. And so you can sort of see this last problem was beginning to cross over from kinematics to dynamics because we're asking about forces. However, if we want to go whole hog into rotational dynamics, as you've seen with kinematics, we provided a rotational equivalent for all the all the kinematic variables. So we had angular acceleration, angular velocity, angular displacement. Obviously, we don't have angular time because it's the same for both, but all the other quantities we changed over. And so when we come to dynamics, we're going to have to do the same sort of things, right? We've looked at Newton's laws, and when we look back at these things, we combined these and produced a relationship between force and the linear kinematic variables. And these were Newton's laws of motion. So the next question we have to ask ourselves is, well, do these things work for rotating bodies, right? If I've got a rotating body, is there some sort of Newton law of motion for rotation? Now the problem is that as they stand, Newton's laws of motion are very difficult to apply. We've got a force acting in a straight line, right? And as you can see, as you rotate, the direction of these lines, the direction of these vectors are continuously changing if you use a linear vector. And when we used our angular variables, we changed our linear vectors into axial vectors, right? So remember we talked about the angular velocity was a vector, but it pointed along the axis, and we had our right-hand rule to determine what the direction of the vector was along the axis. So we want to do something similar for Newton's laws, right? So if we start with Newton's laws, we've got force here, and we've got mass, and we've got acceleration. Now, we know that we can replace acceleration with angular acceleration, but clearly this is not going to work, right? Because if you think about what's happening here, the direction of this vector is along an axis. So if I have an object sitting on a table here, and I provide a force acting in this direction, it causes an angular acceleration about some axis here. So my angular acceleration vector is upwards, downwards in this case, because I'm rotating it that way. So my angular acceleration vector is downwards, my force vector is sideways, and so clearly this isn't going to work because this is at 90 degrees to that vector, right? So this is not true. You can't just do a simple replace of linear velocity with angular velocity. And the reason is because just as we replace this, we also have to replace mass and force. Because if you think about it, in this equation here, this gives us the amount of linear push, if you like, that we're adding. And we need to convert this into how much rotational push we're providing. And similarly here, mass is the resistance to linear motion. It's the inertia resistance to linear motion. But here we're not doing linear motion. We need something that's a resistance to angular motion. And clearly, if I had a heavy weight, well, I don't particularly have a heavy weight, but if I put a weight at the end of my arm and I try to rotate my arm around, it's harder to do that. I mean, if you have got weights at home or a handbell, if you put it out at the end of your arm and you move it up and down, it's a lot harder than if you put it sort of in the crook of your elbow and move it up and down, right? That makes it a lot easier, but the mass is the same. So if we were using something like mass, this wouldn't register as being harder to turn. So we need to have something to replace mass. So what we introduce is something called the moment of a force, right? And what this is defined as the tangential component of a force multiplied by its distance from the axis of rotation. And so this produces something that's akin to how powerful a force is at generating turning motion. Right? You can also define it as the lever arm of the force, where the lever arm is if you take the line of action of the force and the perpendicular distance of closest approach to the axis of rotation. That's another definition, and we'll show next time that those are exactly the same. The only other thing I want to mention before we stop is that there is two pieces of vocabulary here. So there is moment of a force and there is torque. Now the textbook is an American textbook, and it uses torque exclusively when it's describing the moment of a force. Now, coming from Britain, every physicist in Britain refers to it as the moment of a force. When I came here, I was then confronted by these two things of which one I should call it. In Britain, the engineers call it torque, but all the physicists call it moment of a force, and that's what's taught in the schools. So I talked to my departmental colleagues to try and get the right lingo for Canada, and it seems to be the same, Most of them will refer to one of these things as the moment of a force and not as torque, but I'm sure if I went to the engineering department, they would all refer to it as torque. So you need to be familiar with both bits of vocabulary, because certainly the more advanced physics textbooks will often talk about the moment of a force, and also the concept of moments can actually go beyond forces. It can apply to more than forces. So I will tend to use moment of a force. It means the same thing as torque, and you should be familiar with both bits of vocabulary because they're used in different places. Okay, so we'll return to this on Friday, and I'll also be handing out the midterms